Assalamu alaikum. This is Physics 281, lecture number 9. I will talk about the transverse waves, wave motion. Now, let's represent a motion, a wave, a schematic representation for a wave. This is the time, the horizontal axis, and the vertical axis is the amplitude. This is a sine wave. The distance between two adjacent maximum is called a wavelength, and the maximum is the amplitude, called the maximum amplitude. What do we mean by a transverse waves? That's the displacement or the oscillation of the particles are perpendicular to the direction of propagation. An example for this is the string waves we discussed in the previous chapter. Electromagnetic waves are transverse waves. There's also longitudinal waves that in this case the displacements or the oscillations of the particles are parallel to the direction of the propagation. An example of such waves is the sound waves, which is the subject of the next chapter. Now, what do we mean by plane waves? Plane waves, this is a plane waves that the oscillators in a plane of the medium have the same phase in their vibratings. All these masses or oscillators are vibrating in phase. This is the direction of propagation. This is a transverse waves. In this case, the propagation of the wave is in horizontal direction, and the oscillation also in horizontal. All oscillators located on this plane oscillates in phase. Now let's define what do we mean by velocities in wave motion. The first term is the particle velocity, which is the velocity of the oscillator about its equilibrium position. The second is the wave or the phase velocity, which is the velocity with which planes of equal phases or crests or troughs progress through the medium. There is also a group velocity if we have a number of waves with different frequencies or different wavelengths. Different velocities may be grouped and superimposed to form a group. Now, for a monochromatic wave, the group velocity and the wave velocity are the same. Monochromatic means one wavelength, mono wavelength. Now let's derive the wave equation for a string. We already derived this in the previous lecture. Let's take a portion of the string, a delta m, and this portion, the first end is at x and the second at x plus delta x, subject to a tension T. Let's look at the vertical component of the tension here, which is T sine theta prime, and here at the left side it's T sine theta. This is theta. Now, the net force is T sine theta prime minus T sine theta. We can approximate sine theta by tan theta, so sine theta prime is tan theta prime, and sine theta is tan theta. Tan theta prime is the slope at this point at x plus delta x, which is dy by dx at x plus delta x, and tan theta is the slope at the left side, which is dy by dx at x. Now for the right hand side, we write the mass of this portion, which is delta m, times the acceleration, which is d2y by dt square. The mass can be written as lambda delta x. Now we do Taylor expansion for this about x. which gives the first term is dy by dx at x, which cancels by this term, plus the second term, which is d2y by dx squared times delta x, plus the third term and higher order term proportional to delta x squared, delta x cubed, and so on. If we take the limit delta x approaches 0, then we left with this term only. Well, that's t d2y by dx squared times delta x. So delta x cancels from both sides. We finally reach to the wave equation, which d2y by dt squared equal the tension over lambda. Lambda is the linear mass density measured in kilogram per meter times d2y by dx terbium. Now rearrange this equation and make dimensional analysis. We get this is v, which is the square root of t over lambda is the velocity of the wave. Now if we look at this equation, y is a function of x and t. This is the wave equation of a vibrating string. For longitudinal waves in a solid, the elasticity is measured by Young's modulus. For gases by gamma pressure. Gamma is the specific heat and P is the gas pressure. Now let's solve this equation, this wave equation. We'll assume that y is some function f1 of vt minus x, or some function of ft of vt plus x. The first function representing a wave moves in the right direction, and the second represent a wave moves in the left direction or negative x-axis. Now, if this is a solution, it must satisfy this equation. Let's assume that Vt minus x is u. Now, to find du by dx, now it's dy by dx, it's du by dy times du by dx. Dy by du by du is df1 by du times du by dx from here is minus 1. So we get df1 by du times minus 1. Now the second derivative d2y by dx terbi again is minus d2f1 by dy squared times du by dx, which is minus 1. Minus 1 times minus 1 gives plus 1. So we get d2f1 by dy squared for this term. Now let's take the right term, dy by dt squared, and multiply it by 1 over v squared. Now dy by dt is df1 by du times du by dt. Du by dt from here gives v. So we get df1 by du times v, which is v df1 by du. And the second derivative is d2 f1 by d2, this is square, du by dt. Du by dt again is v square. V square df1 by dy square. Now insert this here. We have v square over 1 v square. We left d2 f1 by dy square. That means that the right hand side is equal to the left hand side. The same thing can be done for the second function. Now, the most general solution is the linear combination of f1 plus f2. Now, let's recall that for simple harmonic motion, and we did in chapter 1, we found that y is given by this expression a sine omega t minus phi. Now we're assuming that y has this expression f of vt minus x. But if we look at the argument of this function, the dimensions is length, and the dimensions of the argument of this function is radian. Therefore, we have to convert this into radians. We multiply by 2 pi over lambda. 2 pi in radians, and lambda is length. So length by length cancels, and we left with radians. Now, doing so, we get 2 pi over lambda vt minus x. Now, the dimensions of the argument of the sine is the radians. Now V over lambda times 2 pi is the omega t, should equal to omega t, which means that omega is 2 pi v over lambda. If we substitute for omega 2 pi times the frequency, we get that the frequency is nothing but the velocity v over lambda. This is the meaning of this equation. Now, we have y as written as a sine 2 by vt over lambda minus 2 by over lambda times x. If we compare this expression by this, it means that phi equal 2 by times x over lambda. Now, if we take x equal lambda, it means that phi equal 2 by. So, lambda is the separation in space between two oscillators with phase 2 by, that they are in phase. This is representing the wavelength lambda. So it goes with our definition of lambda at the beginning or on slide number 1. So now this is again 2 by to show that 2 by v times lambda is nothing but omega, or lambda v times the frequency is v. The bracket for the second bracket, we can do the same. This is representing a wave in the negative x direction. Now y, there are many equivalent expressions for y. A sine this, or 2 times the frequency times t, or a sine omega t minus 2 pi over lambda times x. 2 pi over lambda, we define it as k is the wave number, so k is 2 pi over lambda. Now this is the expression for y. In complex form, we can write y as a e to I omega t minus kx for a wave moves to the right or positive x-axis, and y equal a e to I omega t minus plus kx for a wave moves to the left axis. Thank you.